Hi, thanks for joining me. Today we're going to be solving a problem from an area of maths known as probabilistic combinatorics. Now this is really cool because the solution to this problem kind of involves a really slick technique. We want to show that something exists, and the way we're going to show it exists is not by constructing it, but by just showing that the probability of it existing is non-zero. So that doesn't make a lot of sense, but let me state what the problem is and then we'll get stuck right in. So we have s a subset of the positive integers with the cardinality of s being equal to n. So n here is just some finite positive integer. We want to prove that there exists a sum-free subset of s, which we're going to call a, with the cardinality of a being strictly bigger than n over 3. Okay, so a is a subset of s, and a has more than n over 3 elements. What do I mean here by sum free? Well, it's kind of what you want it to mean. It means if I take two elements within A, add them together, I no longer remain in A. So I've just kind of rigorously defined it here. We say that a subset of the natural numbers T is sum free if, when we take two elements A and B in T, we add them up, we get an element which is not in T. So if we take any two elements in our set, add them up, then we come out of our set. So for example, 1, 3, 7 is sum free because if we take any two elements in this guy here, add them up, we're not going to get something that's in the set. So for example, 1 plus 3 is 4, and 4 isn't in the set. 1 plus 7 is 8, 8's not in the set. 3 plus 7 is 10, and 10 is not in the set. Okay, so this guy here is sum free. You can just check all the combinations. However, this guy, 1, 2, 8, is not sum free. And the reason for that is because 1 plus 1 is 2. Okay, and 2 is in the set. So there's nothing stopping A and B both being the same. That's allowed. So if we take an element and double it and also remain in the set, then that set cannot be sum free. So this guy is not sum free, this guy is sum free. So essentially our little problem here is to prove that for any subset of the positive integers, we have for any subset of the positive integers s, we can find a subset A of s which has has large size, so size bigger than n over 3, with A being sum free. Okay, so if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so I should mention that the solution to this is as a result of Erdos, and I think he did this back in the 1960s. Anyway, let's get stuck into the solution. Let's just label the elements of S, S1, S2, and so on, all the way up to Sn. Okay, next thing we're going to do is choose a prime number P, and this is going to be a big prime number, and it's going to be bigger than twice the maximum element in S. Okay, so of course there are infinitely many primes, so we can certainly choose a prime that's bigger than twice the maximum of S, but in fact we're going to insist a further condition that P is 2 mod 3. So P equals 3k plus 2 for some integer k. Now you might ask yourself, well now is this possible? And yes, it is possible. There are infinitely many primes which are 2 mod 3, and in fact in a previous video which I'll link in the description, I proved that there are infinitely many primes that are 1 less than a multiple of 6, and of course if you're 1 less than a multiple of 6, then you're 5 mod 6, but then you're also 2 mod 3, so there are infinitely many primes of this form as well. So we have S being the elements S1 up to Sn, P being a big prime number which is 2 mod 3, and we're going to let it just equal 3k plus 2. The next thing we're going to do is consider this set I. Okay, and it's just going to be k plus 1, k plus 2, all the way up to 2k plus 1, like so. Okay, well, so how big is I? Well, there are k plus 1 elements in, k plus 1, k plus 2, all the way up to 2k plus 1. There are k plus 1 of those guys. But also, what's really nice about I is sum free, but in fact we can do better than that. I is sum free mod P. So if you look at everything mod P, and then look at, take two elements in I, add them up, look at that mod P, we're also going to stay away from I. And we can prove that. So if we take two elements from I, A and B, well, A and B are certainly going to be at least k plus 1 each. So if we add them up, we're going to get at least 2k plus 2. Okay, well this thing here is simply bigger, well, is equal to 2k plus 2. So we're going to be at least the next element along, so we're going to certainly be out of this set. However, you might worry that, well, if A and B are big, so they're near this side of the set, when we add them up and then look at that mod P, perhaps we can wrap round and come back to the start of the set. But in fact that's impossible as well, because A plus B is going to be at most 2 lots of 2k plus 1, which is just 4k plus 2, but 4k plus 2 is simply 3k plus 2 plus k, and 3k plus 2 is simply p, so this is p plus k. So if we consider it mod p, this guy here is going to be at most k, so it's going to be just to the left of this guy here. So I is really nice because it's sum free normally, and you can check it's sum free normally because if you take any two elements, say a and b, they're both going to sum up to at least 2k plus 2, and that's certainly going to be on the right of this guy. Okay, so it's certainly sum free normally, but in fact, by this argument here, it's also sum free mod p. So we found a guy I, which is sum free mod p, and I guess one thing we should notice is that the size of I is k plus 1. So the size of I is k plus 1. And if we have a look at what we have here, p is 3k plus 2, so this is roughly 1/3 p. Okay, so 1/3 p is roughly the size of I. I is sum free, it has size roughly 1/3 of p. What we want to do is kind of show that not I is the set we want, but something similar to I, and I'll get into what I mean by similar in just a second, is the set that we want to use as our subset A of S. Anyway, let me clean up the whiteboard and we'll continue. Okay, so we just showed that I is a sum-free set mod P. The next thing we want to do is introduce a uniform random variable R. So R is going to be a uniform random variable from the set 1, 2, 3, and so on, all the way up to p minus 1. So it's a discrete random variable taking each of these values here with probability 1 over p minus 1. So nice and uniform. The next thing we're going to do is consider the random variable t, and in fact I'm going to denote it with subscript I because we're going to use, there's going to be n random variables, one for each of the s's here, and it's simply going to be r, which is a random variable, times si, which is a constant. So si is a constant, and r is a random variable, so in particular ti is going to be a random variable. Now r is uniform from 1 up to p minus 1. Now si, well remember si is from this guy here, and in particular si is going to be less than or equal to the maximum element in S. And remember p we chose to be bigger than 2 times the maximum element of S. So in other words, all these si's here are quite small compared to p, but in particular they're strictly less than p. So they're going to be one of these elements here, and in particular then they are co-prime to p. So si and p share no common factors, i.e. si is not a multiple of p. And yeah, I guess si, one thing to note is si is not 0 either, because we insisted that s is a subset of the positive integers. So because r is a random variable on 1 up to p minus 1, and si is between 1 and p minus 1, when I do this times this, and look at this mod p, so perhaps I'll just put a little p here, because we want ti to be between 1 and p minus 1, ti is certainly going to be between 1 and p minus 1, but in fact it's going to be a uniform random variable, okay, in 1 all the way up to p minus 1. Okay, because si here is co-prime to p, which means it's kind of, you know, like I don't want to use the word generator, but if I do si, that's going to be distinct from 2si, and that's going to be distinct from 3si, and so on, all the way up to p minus 1 times si, when I look at those mod p, and I'm going to get each of these guys here exactly once. So if you know, I guess that's one thing, going from here to here, if that doesn't quite make sense, just perhaps pause the video and take a minute to understand why that's the case. R is a uniform random variable, so ti is also a uniform random variable on 1 all the way up to p minus 1. So ti is a random variable. Well, what's the expectation, or sorry, what's the probability that ti lies in I? Because, well, notice that I is k plus 1 all the way up to 2k plus 1. It's certainly going to be a subset of this guy here. So there's probably a decent chance that ti is going to be in I. So the probability that ti lies in I. Well, notice that this guy here is a subset of this thing here, because the biggest, you know, we go from 1 all the way up to p minus 1. P minus 1 is just 3k plus 1, which is clearly bigger than 2k plus 1. So I is certainly going to be a subset of this guy here. So the probability that ti lies in I, because everything is uniform, we just simply have, that's the cardinality of I divided by the cardinality of 1 all the way up to p minus 1. Okay, because for each of these guys here, perhaps let's just write this as p minus 1 because there are p minus 1 elements in the set. For each of these guys here, there's a 1 over p minus 1 chance of ti being that guy, and I has size cardinality of I. This thing here is k plus 1 divided by p minus 1, which is 3k plus 1. And notice that this guy here is strictly bigger than a third. Okay, so the probability that ti lies in I is k plus 1 over 3k plus 1, and you can just cross multiply to verify this last inequality that this guy here is strictly bigger than a third. So ti is a random variable, and the probability that it lies in I is strictly bigger than a third. The next thing I want to do is introduce another random variable and show that its expectation is at least or strictly bigger than n over 3. Okay, and this third is going to become very useful in just a second. We're essentially just going to multiply this by n. We're going to show that this random variable has expectation n over 3, so that means there must be kind of some state in which it has value bigger than n over 3, because otherwise the expectation would be less than n over 3. Okay, so we're going to show that it has a state with size n over 3, and that will be the one that we use, or we're going to use that to give us the A, which is going to give us the subset of S, which is sum free and size at least n over, or strictly bigger than n over 3. Anyway, let me clean up the whiteboard and we'll continue. Okay, so the random variable I want to introduce is x, and x is simply the number of ti's in I. So we have these random variables ti, some of them may be in I, we're just going to count the number that are in I. But another way of writing it is this guy here, the sum from I equals 1 to n of the indicator of ti being in I. So this guy here is just a function, it's either 0 or 1, it's going to be 1 if ti is in I or 0 otherwise. So we simply go through all the i's, and I go through all the ti's. If they're in I, we're going to add 1, and if they're not in ti, we're going to add 0. So that's simply the same thing as this guy here. The next thing we want to do is compute the expectation of x, as I said. So the expectation of x is simply going to be the expectation of this guy here. But now we can use linearity of expectation to swap the expectation sign and the summation. So this is in fact just the sum from I equals 1 to n of the expectation of the indicator function of ti being in I. Well, what is the expectation of the indicator function of ti being in I? Well, that's going to be 1 times the probability that ti is in I plus 0. Well, that's exactly the probability that ti is in I. So this thing here is just the probability that ti lies in I. But we just showed that that guy there is strictly bigger than a third. So this thing here is going to be strictly bigger than the sum from I equals 1 to n of a third, and that is just n over 3. So we have this random variable x, which is simply the number of ti's that are in I, and we've just shown that the expected value of x is strictly bigger than n over 3. And I guess one thing I should make clear is x here is certainly a random variable, because each of the ti's are random variables. So, you know, if we were to do this, run this a bunch of times with different values of r, we'd get different values here. So it certainly is this random variable, but the expected value of x is strictly bigger than n over 3. So that tells us there exists some r0. So r0 here is not a random variable, it's just a number. Maybe I'll use a lowercase r to make it perfectly clear. There is some r0, which is in 1, 2, all the way up to p minus 1. So one of these values here, such that with that r0, if you were to use just ti equals r0 times si for each of these guys here, then work out the number of ti's in I, so compute that kind of value of x, that x0, we would then have that x0 is strictly bigger than n over 3. So x0 here is not a random variable, x0 is simply the number of ti's, which is just going to be r0 times si's in I. Okay, so let's just quickly go over this again. Because the expectation of x is bigger than n over 3, that means there's kind of some states in which it is bigger than n over 3. Because I guess, if you think about this, if we have a random variable x on the real value and it takes, you know, if we draw its probability sort of thing, it has certain probabilities, say, you know, it takes this value, which says minus a half, with something, this guy here is minus 1 with some probability, this guy here is a half with a certain probability, and so on. We look at its expectation, say the expectation is a tenth. Okay, the expectation, mu, has to lie between the smallest value that it can take, minus 1, and the largest value it can take, a half. So when we compute the expectation, which is what we did here, x, we got that it's something bigger than n over 3. So that means that there's got to be a state in which it takes value, which is at least its expectation, which is strictly bigger than n over 3. So that's kind of what we've done here. That means that there must exist some R0 in the set 1 up to p minus 1 such that x0 is strictly bigger than n over 3, where here x0 is just the number of ti's. If we define, say, ti to be equal to r0 times si, so lowercase t now, so the number of ti's in I. Okay, so x0 here is the number of these ti's in I. Hope that has all made sense. It's a really nice trick using just using expectation, knowing that because the expectation of x is something, we've got to have a state in which is at least that something. Okay? Anyway, we haven't finished yet. I'm waffling now, but let me clean up the whiteboard and we'll continue on to the last bit in showing that we can find a sum-free subset which is of size bigger than n over 3. Okay, so we've shown that there exists this R0 in the set 1 up to p minus 1 such that this guy here, this set, has size bigger than n over 3. So this set here is just a set of si's for which si times r0, when I look at that mod p, it's going to be in I. Okay, so this guy here has size bigger than n over 3. And what we're going to do is just let this guy be our set A, because it has size n over 3, so the only thing we have to check is that it is sum free, and that's pretty clear because if we take, let A and B be in A, well then A is going to be equal to Si for some I, and then B is going to be equal to Sj for some j. It could be that I and j are the same, but then A plus B, suppose A plus B is in A. So suppose for contradiction, A plus B is in A. Well then that means that A plus B, which we know is just Si plus Sj, would be equal to Sk for some k. Okay, but then if we just multiply this guy here by R0, we get that R0 times Si plus R0 times Sj is equal to R0 times Sk. And then what we're going to do is just look at this mod P. Now, this guy here, R0 Si, is in I. R0 times Sj, that's also going to be in I. And because, well, essentially because Si, Sj, and Sk are all in A, then that means that R0 times themselves are going to be in I. But we showed earlier at the start that I was just a sum-free set mod P. So in fact this is impossible because we've already showed that I is a sum-free set mod P. So that means that this is impossible. So that means that we've already arrived at our contradiction. And hence A is indeed a sum-free set, and it has size strictly bigger than n over 3, and also it's very clear to see that A is a subset of S because each of them are just SI's. So we've solved our problem, we've found a subset A. And what's really cool about this is it used, kind of counterintuitive, it's not really clear why you should start with this prime which is really big, and then why you should introduce these random variables, but it all works really nicely, and this all falls into an area known as probabilistic combinatorics, which kind of got introduced, I think, around the 1950s. So there were a bunch of these kind of new or newly thought out techniques and ideas brought about at the time, which people hadn't thought about before, and it allowed us to solve these problems in this really slick kind of way. Anyway, if you've not seen this before, I hope you did enjoy it. I tried to explain it as best as I can, but sometimes it does just take a couple of times reading through it, looking through the arguments to get, looking through the arguments over and over to get your head around it. Anyway, I hope you have enjoyed this video. Thank you for watching. I'll catch you in the next one. Have a great day.